All right, so let's say you're given this ellipse here, and the question asks you to find eccentricity E of the ellipse. To start, what is the eccentricity? Eccentricity is a dimensionless number that describes how much a conic section deviates from being circular. So some examples are for circle, E is going to be equal to 0. Since a circle is perfectly circular, eccentricity equals 0 makes sense. And I also note some other conic shapes like the ellipse, parabola, and hyperbola. These are the eccentricity values for these conic shapes. The equation for the eccentricity is going to be equal to the distance from a point on the curve to the focus divided by the distance from that point to the corresponding directrix. Now, what is the directrix? The directrix is the reference line which helps determine how stressed the curve is. This can be determined from the equation describing the shape. You can look at the equations representing the typical conic shapes. So for a circle, it's going to be x squared plus y squared equals r squared, because if we look at a circle, any point r can be described by the equation. For an ellipse, it's given by this equation here. We have a and b, where a is the semi-major axis and b is the semi-minor axis. And so we can describe any point in the ellipse with this equation. And then for a parabola, it's given by this equation here, where the y is the dependent variable. And this is because if we look at this diagram here for a y-dependent parabola, this is commonly used to describe a planetary orbit. For a hyperbola, it's given by this equation here. So for this general hyperbola that we draw on the right-hand side, we can identify this horizontal distance from the origin as a, and then this vertical distance from the origin as b. And so a and b are determined by the lines on the graph, and these lines are a function of the angle and the focal length. If we apply this to our example, we can find the eccentricity by applying the equation. The distance from a point to the focus, if we pick the origin, we can identify this distance as c. The distance from that point to the directrix. For a ellipse, this distance is going to be equal to a. The eccentricity is equal to c divided by a. But what is c? We can find this by taking point 0b. So if we look at our graph, this point here is going to be equal to 0b. That means that the distance from this point to the focal length f is going to be square root b squared plus c squared from the Pythagorean theorem. We can apply a key property of ellipses, and that's any point. Distance PF1 is equal to distance PF2, which is also equal to 2a. And our point PF is equal to square root b squared plus c squared. In our example we took before, we can use this to solve by equating PF equal to 2a. We can isolate for c. With this c value, we can plug it into the eccentricity equation. And if we do that and we simplify, we find that eccentricity is equal to this. So this represents the eccentricity of the ellipse, and this makes sense because if we take the case when b equals a, our ellipse is going to transform into a circle. Since a is equal to b, we know that a circle eccentricity is equal to 0. And if we apply b equal to a to the equation we just found for the eccentricity, we can find that this fraction is going to be equal to 1, and then 1 minus 1 is equal to 0. So we find that the eccentricity does turn into the eccentricity of a circle. So that means that our equation we found makes sense.